So today's topic is about integration by parts, where you need to do like substitution in between. So this is especially useful when you're taking like calculus 2. So most of you probably know this formula, right? The integration by part formula is integral of u dv is equal to uv minus integral of v du. Now looking at this equation, what does it mean? So it means that like once you can write an integral in the form of integral of u dv, you need to integrate dv into v and differentiate u into du, right? So that you can rewrite it in terms of uv minus integration v du. So one part of it you need to differentiate, and the other part of it you need to integrate. And this is where the usual DI method, the DI table method, comes into play. But today I'm not discussing about this method because it has been covered by many YouTubers, especially Black Pen, Red Pen. You know him? Let me just write it here. Yeah, so you can just search Black Pen, Red Pen, DI method, and you can easily see one of his explanation on the table method. But today we're trying to solve a different kind of integral where it's a bit tricky. For example, this one. Right? Let me just move it somewhere else. So in this case, when you're trying to integrate sine x squared, like it's not that simple, right? You need to actually substitute dx with something else. So in this case, you want to rewrite it in terms of dx squared. So dx is equal to dx squared over 2x. Then you can rewrite the integral as sine x squared over 2x dx squared. Now obviously you can't just solve this by itself, right? That's why it comes with the other part, the x cubed part. So now we're talking about like how to combine this substitution thing into the DI table method. So if you recall, the DI method has two columns. One is where you differentiate the terms, and one where you integrate the terms. But for this method where you need to do substitution, I would like to add a third column. Like I will call it a variable column, the variable, which is the actual variable of integration that you're integrating with respect to. So in this case, we have an equation that we're trying to integrate, which is x cubed sine x squared dx. Now after doing the substitution, you can, well, let me just write it again. Dx is equal to dx squared over 2x. You can think of it as writing it in terms of u dv. So in this case, this is u and this is dv. But we don't like this equation because you just can't integrate this. So we would like to rewrite it in another way as x squared over 2 sine x squared dx squared. Because now we have changed the dx with whatever that thing is. Okay. So now we can change the label for u and dv. This is u and this is dv. So essentially what we're doing here is like we're rewriting the equation. But I'll not like to do this externally, like outside of the DI table, you know. I would like to do it inside the DI table. That's why I like to add the third column. Let me just show you how to do it. So first, you just write your initial integral. Like, you know, you'll differentiate this part and you'll integrate this part. And you know your variable of integration, which is dx. And now you just rewrite it underneath this initial one. X squared over 2. You'll differentiate that. You will integrate sine x squared, not with respect to dx, but with respect to dx squared. Holy. Now, here's where the tricky part comes in. In order to fully understand why this method works, you need to look at the formula for integration by parts again. So on the left side, we have u, right? And on the other two columns, this is the u column and the other two columns are dv. When we look at what's happening to u, you're trying to differentiate it, right, into the u. So in this case, we have x squared over 2. We're trying to differentiate it, but x squared over 2 is equal to u. What is du then? It's the derivative of x squared over 2, right? But what do we differentiate with respect to? That's a good question. The answer is you can differentiate it with respect to anything, but in this case, it's just trivial, right, to differentiate with respect to x. So I will just differentiate it with respect to x now. Du over dx is equal to what is it? It's just equals to x, right? Wait, let me check my answers first. I'm starting to forget how to do this. Okay, so it's x. So now we can write du in terms of x, which is the derivative of u and dx. So this whole table thing is just like a way to rewrite the equation, and like you put segments into it. You know, like that's why we have this lines. It actually means nothing. It's just like to segment it. You know. So now that you know what du is, we just need to find v, this v here, which is just the integral of dv. So in this case, dv is sine x squared dx squared, right? If you integrate it, it's just negative cosine x squared. Well, there's a plus c, but for this case, we'll just ignore it because you can just add it later in the final answer. So the column here is udv. The column underneath it is where we're writing v du. This part. This part is v du. This is udv. Well, we just have two different rows because we rewrite the equation. Okay, so now we're trying to write v du into this thing. So what is v du? We know that du is x dx and v is negative cosine x squared. So we know that v du is equal to negative cosine x squared x dx. But remember, we're trying to write it into this table. So I think it's better if we write it as x and then negative cosine x squared and then dx, right? This whole table thing is not like an absolute kind of truth. It's just a way to write. So what do we put here? X negative cosine x squared and dx. Now you see the pattern? You just repeat this until you get the answer. Okay, let me just try to complete the rest of it. So let me just clarify some more things, okay? Where does this dx come from? It comes from this. When you differentiate it, you will have the derivative and the variable that you differentiated with, which is dx. So if you differentiate with respect to x squared, it will be a different answer here. It will be x squared here. You know, but in this case, I'm choosing to differentiate with respect to x because it's easy, you know. And then, of course, you can just do the substitution again as this will be half negative cosine x squared dx squared. Let me just erase all of these things. So now we can do the differentiate integrate again. This time I'll still differentiate with respect to dx, so that will be 0 dx, and integrate this thing, so it becomes negative sine x squared. Okay, now that we've completed all the, well, of course we have 0 here, we can't differentiate anymore, so we're complete, we're done. But how do we get the answer? What an interesting question. Now, I can just tell you how you can get the answer, but I think it's better for me to explain this, as it will give you an idea like why this thing actually works. So if you look at this equation here and this equation here, you can think of it as u dv, right? Which is this initial problem here. And I just rewrite it into another form of u dv. And these ones are the VDU, which is this one. So we know that this part is for u and this part is for dv. So if you look at the equation here, it says uv. Which one is uv? If this whole thing is u dv. Let's just erase this. I think it doesn't make a lot of sense, right? So of course, you know that this is u, right? And this is dv. What about this? It's v. It's the integration of this. And this one, let me just use red. These two things, x and dx, they are du. So what is uv? It's this, x squared and negative cosine x squared. So you take this part diagonally like this. That is the uv. That is the uv for this row. So for this row, the first row, you got the uv already, and then where's the minus integration of vdu? It's the row beneath it, right? It's this row. So for the row below it, you want to find the result of it. I know this is a bit complicated to think about, but this is where the sign thing in the DI method comes in. Like this one's positive because you've got the UV, and then this one's negative. Why? Because look at the sign here. It's negative. So once you find the answer to this, it's like another integral, right? This is like recursion, you know? So once you get the answer, you will get a minus sign to it, okay? hold on there. I'm still trying to explain this. So positive, this is going to be negative because of the sign. And where's the uv for this integral? Well, we rewrite it. Where's the uv again? The front part here, it's this thing. So as you can see, it's just like the usual DI method, but make sure to be careful here because we have two different equations, right, for each row. So the answer that you will choose from is the second equation in that particular row. You know, like this is the first row and this is the second row. So the second equation, and then it crosses diagonally over this horizontal line. Yeah. So the last one here is gonna be positive again because, you know, so essentially the answers, all of the answers that we're getting here is all of the UVs, because eventually this VDU, it will decay, you know, so it's like a bunch of recursion, like it's UV minus integral VDU. So at each step you just take the UV, and then this is another question, which is why we write it below, like it's another integral, you know, like another problem. So like recursion, you know, right, you have initial problem and then you can have the recurrence where you turn it into an easier to solve problem. Like in each step here the problem gets easier and easier, right? Yeah, so the answer is negative x squared over 2 cosine x squared negative, so it's plus half sine x squared. Remember to add the integration constant plus c. So that's it for this video. I hope you can understand it and apply it in your exams. I guess it's a very fast technique.